math. Turns out that somebody named Riemann had done four-dimensional geometry just for fun. Mathematicians do that, they're playful, right? It's like, here, this will really wreck someone's mind, right? And Einstein was having difficulties. A friend of Einstein said, read this guy's book. So Einstein reads the book. He even does the problems at the end of the chapter, right?
Just like a kid.
Yeah, you know, and he learns four-dimensional geometry and bases a theory called general relativity on this. This is like one of the masterpieces of modern physics. Now, let's go back to 2 dimensions because my brain's hurting trying to picture 3 dimensions bent in a fourth. Did that hurt you? Okay, so let's go back to this. This is what we can picture. Let's take this classroom, throw everything outside, not really, okay? And let's fill it with water this high and stretch a sheet of rubber across the water. Are you picturing that? A very large waterbed? How are you picturing that? That is flat space-time. Now let's take a shot put and put it here. Isn't that going to make a depression shaped like this to the shot put? Right? And a 10-pound shot is going to make a deeper depression than an 8-pound shot, won't it? Yeah. And one that's made of lead, if it's the same size as a shot put, would have considerably more mass and would make it even the side steeper. Now think of that shape. Do you guys ever go to OMSI and they've got the little thing where you can roll the coin in and it goes round, 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 yeah? A coin trying to go straight on a 2-dimensional surface is forced to go in a circle by the curvature of that 2-dimensional surface, yes? This is what Einstein says is happening with planets, okay? This thing here, let's picture this, start this over again. This is, we're looking down into one of those things that collects the coins, a gravity well, right? Okay? There we are, and we just happen to have the right velocity to go in a perfect circle around that, yes? Okay? Now, I'm going to start slowing down. As I slow down, what do those coins do when you slow down? They get closer and closer. What do? Do they stay at the same speed? No, they go faster and faster. I'm just hitting the R key over and over again to simulate friction, right? What do? Don't they go crazy? They're like, ah, whoa, 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 whoa. What's it doing? I have no idea. It's just calculating numerical errors, right? So does that work too? Does that work too? Yeah, this notion of that we're looking down into it. Let me show you another thing, okay? And this is the greatest demonstration. It sits down here all year long. When I need to make this particular point about general relativity, I bring it out. Okay, this is the wrong shape, isn't it? It needs to be shaped this way, doesn't it? But this works, right? The marble trying to go straight, because of the curvature of the surface on which it's traveling, goes in a circle. Yeah? By the way, the shape of this one, if it's a parabola, the period is not affected by the radius. Listen to it. I can spin it faster and faster, right? And until it leaves, right? I can spin it slowly, and it's 1 and 2 and 3 and 4, and I can spin it faster, and it climbs higher up the wall, but it's the same period, isn't it? That's a little bit crazy, right? But obviously, with planets, it's affected by that, right? It's affected by the radius. So let's draw a picture of an Einsteinian universe, right? Here's space-time, flat space-time. Here it is curved. Here's the Earth, maybe, right? Like that. Now, of course, we don't see this curvature because we don't see, this is like the 4th dimension to us. We can't picture this. Like smoke coming out of, right? Okay, but picture this, right? Now if you're in orbit, you're like, maybe if you're in elliptical orbit, you're rolling down lower where you go faster and closer, and you get up higher where you're slower, right? But farther away. Does that make sense? Does that work for your brain? Okay, now, once you've developed this concept, you can develop the concept of escape velocity. Have you heard this? The escape velocity from the surface of the Earth is something, right? Yeah? Have you ever heard that figure? Okay, escape velocity is basically when you have rockets, it's kind of a ridiculous concept. Escape velocity is this. If you were to remove the atmosphere of the Earth, which you would surely need to do this way, and you fired someone straight up out of a cannon, this is the speed you would have to give them so that they wouldn't come back to Earth. You could do it from the moon. The moon has no atmosphere, and you could fire a rifle straight up. At low speeds, the rifle bullet would come back down. At high speeds, it would go away, and when it was infinitely far away, it would be moving really fast. The escape velocity is that minimum speed you can give it, and it won't roll back down the hill. It won't come back to you. Well, how do you find it? Well, you just keep shooting it slower and slower. Load your your rifle with less and less, gunpowder or something like that, right? Okay? And so eventually you'd find that. Well, think about this. If this was a hole in like a miniature golf, right? Don't you see if you try to hit it off of here and you're hitting it up the hill, if you hit it slowly, it rolls up, comes back down, right? If you hit it too fast, it gets to the level and it's going really fast out here. But isn't there some speed? This never really, by the way, gets totally level. It's always sloping upward, just, minusculely, right? The perfect putt, the escape velocity, is the speed you hit it with, where it comes out here and it just goes slower and slower. No, there's no friction, right? It just goes slower and slower. Its velocity approaches zero as you approach infinity distance from it. Or maybe when you're a kilometer away, it's not moving or something like that, If it's a golf course thing, right? If you're a megaparsec away or something, right? Anyway, that's the Einsteinian model. Whatever it is that you need to use, this is what you do. You just picture that in your mind, right? I'm going to speed up, right? Well, if I speed up, I fling myself out. Thank you, sir. I fling myself out. I slow down because I either went uphill or it's conservation of angular momentum, right? Okay. And if I slow down, I roll to a lower thing. Watch this. Everybody cheer when it goes through that little gap. Sudden burst of, yeah! Let's do it again. Let's do it again. You got to wait for it. Random cheering, loud, so the people that are sleeping are suddenly startled awake. Are you ready? Here it comes. Hoot and holler when it goes through that little gap.
Can't see it.
Ah!
It's like the wave.
Here it comes again. Here it comes again.
Here it comes.
Here it comes.
The wave.
Be the first one to yell. Ah! Okay, now I'm going to slow down. Slowing down brings us closer in. When we fall closer in, paradoxically, we speed up. Yeah? Isn't that beautiful? Applause for physics.
So it's linear velocity.